Now let's talk about some of the real examples and understand how these systems work. So the very first topic I want to discuss briefly is power grid versus smart grid. So again, it is used to be called power grid. Yeah? Many people still say it power grid. There are countries where we have only one grid. There are countries where we have multiple grids. If country is big enough, they might have multiple grids. Earlier, these grids were separated from one another. So we have a one grid that is fulfilling the demand in one region. We got another grid in that region, and so on. Now we have interconnected all grids. So that if that grid is not enough, doesn't have enough supply to fulfill the demand in this region, we can pass the energy from the another region to fulfill that demand. That's why we have all the interconnected grid. Yeah. Smart grid, since as I said, we are developing smarter grid, we are deploying number of devices which are smart in nature. They can handle data at large, they can process data, they can compute by itself, they can make certain decisions, and so on. So we start calling it smart grid. Yeah. One nation, one grid. So that's what I'm saying now. All the grids have been interconnected, so that if there's an attack in one part of the region, one part of the country, you can fulfill that demand from other grids. Yeah.
Sorry.
Okay. Centralized versus distributed grid. So what does it mean? Centralized grid, there's a one grid that is covering the entire region, yeah, giving supply everywhere. Now we have a concept of distributed grid. Why? What are the drawbacks of a centralized system? Exactly, single point of fail. Yeah. If you have everything on one device, what if that device is down? Everything will stop. So that's where distributed system comes in, saying rather than having everything on one device or one system, consider multiple devices, put your data, distribute it or replicate it, yeah, so that there's no single point of failure. If someone attack one of your device, other device still there to help you. Now when you, for example, we are in India, when you say, when I want to know what is happening in the US, yeah, so I wanted to know their, or I wanted to have access to their, let's say, National Security Agency, so I will say NSA, I'll search on Google. This will help me to connect to their website in the US, right? So what happens? When you open Google, it will say google.co.in. Yeah, when you say NSA, click the link, what happens actually? So what does it mean when you say google.ac.in? Yeah. So Google has their servers in every other country almost. When we write any query on Google, your request is being sent to the server, Google server, which is in India. Yeah. Now the server looks at query. Query is trying to retrieve a web page from the US. So it cannot find from its database. It can't handle it. Then it will connect to the server from the server in India connects to the server in the US and saying there's a query, you have to answer it. Yeah, and that page is fetched from the server in the US to the server in India and then forwarded to you. So that's how you are able to see these things. So that's where the distributed system actually work. You don't, because if you're putting everything in one place, it might be slow. A lot of queries, your system might slow. On the other hand, if there's an attack, everything will be down. If someone is attacking on Indian server, for example, Google server, by the way, their servers or capacity is really huge. Even if you're flooding them, if you open thousands of tabs on Google, search whatever you like, still safe. They're still safe. But in worst case, let's say if someone attack a server in India, they can still fulfill from other server. They have multiple servers. And depending on the scenarios, they might also keep some redundant data. If you want to know, let's say, about the Google, so they might have some data sitting at every server, which is redundant data, but then they just want it to reduce congestion. So if you are requesting the same data from India, you can get from Indian server. Somebody in China, they can get in, and so on and so forth. But if you are looking for more specific query, then they will connect within their infrastructure, server to server, and then give you that. Then physical attack versus cyber attack, we already talked about. Earlier, we used to have physical attacks where people were talking about tolerance, if there are fault, if there are physical issues, disruptions, how you handle this. But now we are trying to understand how cyber attack can influence the smart grid practically. What kind of attack we should consider as a critical attack that can really create a blackout and so on. So we talked about this yesterday. I'll talk a little bit more. So this is the power generation. So as I said, there are different ways how can you generate power. So earlier we used to have either oil, coal, petroleum, other things. Now we are talking about more on renewable energy sources like wind turbine or solar panels and so on. So you got power generation through power transformer. You get power transmission. So these big towers, we talk about this, and this power reaches to the substations. Substation, you got other devices, for example, transformers to step down it, and then the appropriate level of the voltage depending on which country you are living in. It reaches to your home and buildings and businesses. Now the question, and now we are also having, for example, electric vehicles, scooters, cars, and so on. And all the countries, like all the big countries at least, are planning to have electric-based systems in the next 20 years or so. For example, the UK, they have, I guess, 2040 or something deadline by which they say we will stop all the petrol diesel engine. So there won't be any new petrol diesel device, car or vehicle in the market. So new device will all be electric. Why? Carbon emission is one of the reasons, yeah. And also the cost. We'll talk about cost later on. So let's say you got electric vehicle as well. So you can charge it at your home. You have a connector where you can charge it. Then you got a control center from a company. So if let's say in India we have 3 main distributors for electricity, they might have their own control center. They might they will have their own substations and so on. So they will have their own setup. Every company has their own setup. So at control center, you got SCADA systems, you got different servers, you got operators sitting in control center looking at the big screen, what's going on. Yeah. Control center receives data from substations. So I might have multiple substations. Control center receiving data, wireless, wired, depending on the way it's been configured. Sensing data here, processing it, running all the algorithms, and then understanding what's going on there. Yeah, what could be the demand in this area of a city X, for example. So demand might vary from city to city, region to region. If this is industrial area, that might have a lot more demand compared to other regions. So this is how kind of typical scenario look like. Now, and kind of a centralized power system where you have a power generation, transmission network, distribution network. Now what we are talking about is more distributed in nature. Why? Everybody is relying on power grid. Now there's a concept, something called microgrid. Have you heard it? Microgrid? So what is microgrid? which is a micro version of a grid. I might have a microgrid at this campus where I can supply all the electricity through that. I might create solar panel, wind turbine, whatever, to generate the electricity, storing it somewhere, and then connecting it to all the labs, all the lectures, and to this building. So I'm not relying on the centralized national grid. If that grid is down, I'm still kind of have worst case scenario, still have some backup. Yeah. So that's how, and we believe that in the future there will be demand will increase. It will not reduce anyway. It will just keep increasing, keep increasing. So the grid needs to produce more. We need more power generations. There will be a lot more devices will be connected, a lot more demand in the future. And that's where people are saying you should have distributed systems. Yeah, government is, I guess, supporting subsidies for solar panels you can have on your home, and so why? So that you can sustain it. You can use solar energy to generate electricity, power for your home, and reducing the load on the grid in some way, right? So that's where we are heading. That's why people are saying there are number of energy sources through that we can generate energy, and we should be at least start utilizing this at local level. There are areas where there's no electricity, there's no lines in rural areas, yeah, where you can set up these kind of things. You can have a solar panel, you can have a small grid, microgrid, you can connect to local networks. Yeah. The way it looks for defense area, for example, remote areas where there's no electricity, there's no line. These kind of setup can help them. If they're living in a place where there's wind speed is too high, they can have wind turbine or so. Through that they can generate power, store it at local level, and use it. Now let's talk about some cyber aspect of it. So if you look at the previous attack that have been targeted power grid. So one of the examples is UK power grid. Reportedly at risk from rogue nation state and opportunistic hackers. Another scenario says energy firms point to hacker after Kyiv power outage. Now everybody knows about Kyiv because of the invasion. It's in Ukraine, yeah, Kyiv. But if you look at the previous attacks, what attacker did is, as I said, a company might have number of substations. And generally when they attack a system, they target remote substation. They will attack very remote station. And generally in remote station, there's only 1 or 2 people there. So there's a small kind of room or cabin where they'll sit. There's a HMI interface, human machine interface, that they can look and set up, send some commands. But on field, there's a huge field, the number of devices deployed, power system, transformers, everything else. And in Europe, mostly in winters, temperature goes really down. In some countries, it's minus 20 even, and so on. And remote part, it's even lower. So if you look at the previous attack, what they did, they intentionally targeted remote substations where there's no manpower or little manpower is available, mostly at night, on days where temperature is really low. Yeah. And one of the reasons is remote substation, possibly they don't have much connectivity in terms of communications, or at night there might be nobody there. Generally, only few people work there. At night, generally they come out because they know in the remote areas there's no huge or high spike of demand. In city, it might happen. Yeah, but in remote area, they can predict what kind of demand will be there for day and night, and it's not huge. So there's nobody there at night mostly to control things. So attacker targeted those places so that control center doesn't know what's happening. They can just disable devices, not receiving anything. By the time you got to know, because since they are so remote and there's no people, by the time people will reach there, attacker can perform the attack. Yeah. So one of the learning is, even if your infrastructure is remote, if it is connected to the centralized grid, we need to take care of it. So some of the attacks were performed where there's no electricity during peak winters. And as I said, we always have a heating in all the places there. Otherwise, you can't survive in minus. You won't be able to do anything. Yeah, there are people who work outside. It's impossible for them to work. Now, there's something called Open Smart Grid Protocol Alliance. So when the smart grid came, the people say, okay, they develop a protocol, they start thinking that since this protocol is used for variety of communication, security is one of the key things, obviously. So alliances, these kind of alliances, generally a group of companies, yeah, which want to work together on some critical issues. And cybersecurity is one of those, where all the companies part of this group, they sit together, once every 6 months or yearly, and they want to understand the critical topics around their infrastructure. Want to have discussion what kind of policies, what kind of regulation should be there, and so on and so forth. So they run a survey in 2021 where they say, regarding smart grid security, which of these issues are top concerns? So they run a survey asking their exposure to ransom, tampering of data or systems, theft of customer information, outrage caused by cyber attacks. Now again, you can see this is kind of different from sector to sector. If it is a financial sector, maybe ransom would be the priority. But here, compromising your data may not affect much. Yeah? What can change it? Outrage. What if there's a blackout? Someone perform an attack, down your system. So companies cannot afford those. It comes to their reputation. Yeah? If a big company is in compromise, if you say there's a data breach at Microsoft, how do you feel? So you see, Microsoft is not safe. If there's an attack on a small company, you can, since it's a small, it's okay. They will learn and do. But the top companies are compromised, it's a bad reputation. In a similar way, if you know Reliance and Reliance, and you have Adani Energies and so on. So the big names being compromised, it goes bad news. And bad news, what? It floods. People might know the good news, but people will definitely know the bad news. So it floods very rapidly. So that's why they say the cyber attack is one of the key challenges for them, because it can impact massively their infrastructure. Second, they don't have enough skilled people. They don't know how to control what to fix. Because most of the people working there are electrical engineers. They're not cybersecurity experts. They don't have a team. They don't know what is penetration testing, what is red team or blue team. They don't know anything. And now they have started, doing things. So it's really important to go for penetration testing, ethical hacking. Invite some company, cybersecurity company, to test their infrastructure, get to know what are the issues. Again, so they also publish a report. In that report, they talk about number of attacks that have been done from 2014 to 21. So it's a 21 report. Industrial, Operational Goal, WannaCry, Lockergona, US Pipeline, and so on. Some of these are ransom attack. And one out of these, the most popular attack was with the Black Energy, with the Ukraine attack. We'll be talking about it in more detail in one of the case studies. So if you look at this, for example, WannaCry, they say the attack was estimated to have affected more than 200,000 computers across 150 countries. It was a so massive attack, and it was having a default problem in all systems. Yeah, recently we heard another news, and there was some issues in Intel chip. So all the computers that we see, most of them comes with Intel chip. So the issue with the chip, that means all the systems are having bugs, having vulnerability. So that's one of the key things. Then people start relying on other companies as well. Say, I don't want all the things from Intel. I want to have some computer from AMD, from other companies. In worst case, I can save some of my part of my system. So if you're relying on one vendor, if that vendor is compromised, everything is compromised for. Yeah. So say open smart grid protocol is primarily used for communication between smart grid devices like smart meters, solar panels, load control models, enabling efficient exchange of data and control commands within the smart grid systems. So this protocol was its application layer protocol developed by Energy Service Network Association in 2010. It becomes a standard, European Telecommunication Standard Institute 2012. So again, there are a number of standardized bodies around the world, mostly European and Americans. Yeah, so American body mostly it comes from NIST, National Institutes of Standards and Technology, NIST, and then European have their own for telecommunications and for other things. So they say this OSGP protocol used in the devices sold by OSGP alliances or network energy services. Now, when this protocol came, there were so many vulnerabilities in these protocols because this protocol was designed to exchange data between the devices, power system devices like smart meters and other things. So security was not their priority. But now since we are using as a part of a smart grid, people might exploit these vulnerabilities to target the attacks. So we definitely need to start looking at what are the issues in these protocols and how can we fix them. Now before I talk about these in detail, let's go back to some basics and then I'll come back here. So let's learn something about encryption and how does it, I believe all of you know, but just wrapping up. What is stream cipher? So we know block cipher, stream cipher, yeah, in terms of encryption. What is stream cipher? And how is it different from block cipher? Anyone? Stream cipher, that is streams of bits. Yeah. So the way it works, you have sender and recipient. We know for encryption we need to know a key. You have a text, we call it plain text. You have a key, you apply an algorithm with the key to encrypt data, send it over the network, you apply same key, another key depending on what we are using, the algorithm to decrypt it. So you have an encryption algorithm, you have decryption algorithm, and you're using a key. So in this process, we have a key which is generated by a pseudo-random sequence generator. Now there's another thing to how you generate random numbers. So in security algorithms, there are many algorithms that are using random numbers, right? So that one of the reasons why we do have random numbers, so that it becomes difficult for an attacker to guess that number. Every time when I need to do encryption, I might generate a new number randomly. I don't know, it can pick any number. So I might give a range. I want a number between 1,000 and 100,000. It can give me any number. And every time the number will be different. Yeah? So in a way you can use pseudo-random, which is not completely random, but there are a number of algorithms there that can help you to generate those pseudo-random numbers. So you can use any of the algorithm to generate randomly all the bits one after another. So these bits are not in sequence, but they are random. So you can use pseudo-random sequence generator that can give you key in terms of bits. You have your plain text, which is also in bits. You perform an XOR operation. We know what is XOR? What is the property of XOR? Truth table. It says if both bits are same, outcome is 0. If bits are different, outcome is 1. Yeah? Now this is another thing in most of the cryptographic or mathematical algorithm, XOR is really popular. Why? Why we are doing XOR, not AND or not any other operation? Why XOR? Because the XOR has the property which says if you know, so let's say I'm calling it Y, for example, this outcome. If you know P and S, you can compute Y. Yeah? You XOR these two bits, get this one. If you know Y and S, you can know P by XORing S and Y. If you know Y and P, you can derive S by XORing this and this. And that's the only property with XOR, not any other operators. And that's one of the reasons we do use XOR a lot in those kind of mathematical properties. If you know any two inputs, you can derive the third one by XORing it, right? So in this case, if you know these two, you can derive this one. If you know these two, you can derive this one. If you know this two, you can derive this one. That's one of the reasons we use XOR. Now, on the bits, it will pick one bit of your plain text, one bit of your key, XOR it, get the C1, which is your cipher text. Yeah? And you have multiple bits coming up, and then you're generating cipher text. Similarly, on the recipient, you need to use the same generator that can generate the same key. These should be synchronized. So you need to know at what time this will hear and what time you need to start this process again. And then again, you are XORing your cipher text, and this you get the plain text. So as I said, the property, if you know two, you can derive the third one. Yes, synchronization is really important here. If you omit the synchronization, you won't be able to decrypt it correctly. So you need the same bit of key, same bit in order to decrypt it. What are the applications here? In what application we need a stream cipher? So there's another cipher, we call it block cipher, yeah? Where rather than encrypting one bit, we encrypt the whole block. Yeah? For example, I can encrypt 64 bits, not just one. I can encrypt 128 bits. I can encrypt 256 bits, and so on. So that's block cipher. Block ciphers are also useful. Stream ciphers are also useful, depending on the applications. Yeah? Before we get into this, let's answer some of the questions here. Saying what happens if the block size is too short? I have a message that I want to encrypt, which is of 100 bits. But it says if you are using an algorithm, for example, AES, we know AES, yeah? Advanced Encryption Standard. So there was a data encryption standard and advanced encryption standard. Data encryption standard has been compromised, so we don't use it. AES is considered secure, so we use AES for encrypting data. So in AES, we should have block size of 128 bits. It says you have to have a block of 128 bit, then you can use it. If my message is 100 bit, what's going to happen? Padding. So we use padding. Padding is stream of zeros. So if I message of 100 bit, I will use 28 zeros to make it 128. Right? If block size is too long, I'll break it down. If it is 200, so I will have a one block of 128, and then 200 minus 128 plus padding to make it another 128. Why are most block size multiple of 8? Why we are saying 128, 64, 256? Not saying 200, 150, 78. Why? Yes. A computer works, mostly it does most of the operation in bytes, which are 8 bits. Yeah? So it understands bytes much better than other. If you ask it to do it with 200, it will take a little more time to understand. Yeah? If your native language is Hindi, for example, if you are speaking English, take time a bit. On the other hand, if you are speaking English, you will be much faster than any other language. In a similar way, computer understands bytes much better than anything else. So if you are giving it bytes, it will process it immediately. Otherwise, it will convert, and it will take little time. That's why whenever we generate these kind of for the efficiency purpose, we want to make sure it's always multiple of 8. Okay, let's come back. What are the example of stream ciphers? Stream cipher is really important. Again, it gives you high speed. Stream of bits is coming, and you can just encrypt on the fly. You get the cipher text. Yeah, you don't need to wait for multiple of 128. Weakness. Low security because it's just an XOR operation. If you know 2, you can derive third one. If anybody knows your cipher text and plain text, they can get the key. It's as easy. Synchronization issues. If you miss the synchronization, you won't be able to decrypt it correctly. Yeah. Now application. Video data encryption. How does you get this TV channels broadcasting at your home? So you have to subscribe in order to get channel X. It's all broadcasting, video broadcasting. What is the key? If you have subscribed, yeah, that code. If you subscribe, it will unblock it for you, and you got streams of video. If you haven't subscribed, your plan is expired, it will block it immediately. Sometimes we need all these things in real time, live telecast. Right? If you have subscribed, you can watch live on this program, whatever. We need stream ciphers because number of people will be connected. Yeah, you can't wait data to be stored and encrypt, and it should be on the fly, real time. Mobile communications. When you're calling someone, you don't wait data to encrypt. You just want to call. Now, in previous attempts, when we have 2G, GSM, and other technology, we were using stream ciphers. Now, stream ciphers are not really secure, so most of the telecom algorithms were compromised. Now, all the previous older systems, they have one thing is, all the security algorithms were secret. Yeah? It's like I might have my own algorithm based on XOR, whatever. I'm not disclosing, saying I'm doing some encryption, it's secure. But when these documents were leaked, they find out the security was quite easy to crack. If you understand how they were built, it's quite easy to crack. Nowadays, what we are doing, we are developing system where we are saying we know the algorithm, even the attacker knows the algorithm. However, the process itself is so complex, we are more focused on how we are deriving the keys so that attacker cannot have the same key. And if that is the case, even despite of knowing the process, they can't decrypt it. But in the older systems, most of the algorithms, security algorithms, were secret, and they were not as rigid, as complex as we have now. Satellite communications. Yeah? You need stream ciphers. Now, what are the example of block cipher encryption? Where can we have these algorithms? For example, AES. Have you seen anywhere AES? RSA, you know RSA? What are the example? Where did you see anywhere written that this encryption is by AES or RSA? Or when you go for online payment, yeah, mostly they are using AES or RSA, and sometimes they also written that this is secure. Even if you go to banking websites, they have a page where they describe security of this, saying we are using AES with this bit size, we are using RSA, whatever. Because we don't want this to happen on the fly. You still have few minutes. We can wait few seconds once you click it. Yeah? And within those seconds, it all encryption, decryption, everything takes place. Now, when we do block ciphers, we have certain modes to understand. Have you gone through this? Modes of operations? Yeah? Okay. So there are 5 modes. I'll go quickly. One is called electronic codebook mode, cipher block chaining, cipher feedback mode, output feedback mode, and counter mode. Why we have so many modes? Because we want to send a message. Let's say I want to send a message to my friend, and I want to use, for example, AES. That message is confidential. That's why I want to have encryption over it. I want to encrypt it, send it to my friend can decrypt it. Right? If I'm using AES, AES is a symmetric key algorithm. So generally, if I broadly categorize, we have 2 kind of encryption algorithm. One is called symmetric, where there's a one key, single key, can be used for encryption and decryption. Second is your asymmetric or public key cryptography, where we have 2 keys, every user having a private key and a public key. Yeah? Public keys can be derived, are open to all. Private keys are secret to individuals. Right? So in this case, we are talking about symmetric key algorithm, where The same key can be used for encryption and decryption. Now, one of the difficulty for symmetric key is how you generate or how you kind of making sure that same key is being received by the recipient. Yeah, because recipient needs to use the same key. If I'm generating a key, encrypting my message, sending it, I need my friend to have the same key in order to decrypt it. What are the ways of doing so? How can I do that? How can I send that key to my friend? One way I know is email. I can send an email. If I rely on certain type of email, I can send it. But in terms of these kind of system, I can use something called Diffie-Hellman key exchange. You know? Have you heard Diffie-Hellman key exchange? Okay. So Diffie-Hellman key exchange algorithm allow you to generate the same key. I'm not going to detail, but just understand the overview. This algorithm allow you to generate the same key at both ends. And over the network, you are not sending the key, you are sending some odd number. So let's say there are two users A and B. User A generates some number, compute something on the top of it, send it over the network. This guy also does the same thing, generate and pick a number or do some calculation, and they are exchanging those calculations. And then they are computing something on the top of it. And that will generate the same key. So they are not sending the same key, but they are sending some computation to each other. Even the computation is compromised, no one can generate the same key. Yeah. So those are the ways by which we can again anyway. So let's talk about. So as I said, I have a message to send to my friend. My message is longer. So if I'm using AES, I can send 128 bits maximum in a block. So if my message is 10,000 bits, I have to use multiple blocks. Right? I will create blocks of 128, encrypt all the blocks, send it over the network. Recipient will get all the blocks, rearrange them, decrypt, and then recover the message, which is the standard way. Now, electronic codebook mode is considered one of the insecure mode. It's just there, but we don't use it really. What it says, you got a plain text, you have a key, the mechanism by which we can generate key, but we just want to understand the concept here. You apply an algorithm and get a ciphertext. This is an algorithm that requires two things. One is your message, plain text, or 128 bit, and the key. Similarly, I got second block of my message, to plain text and key. Third block and so on. Let's say I have 5 blocks of message. I need 5 blocks. You know, 1 block input for all and then key. And I get 5 blocks of ciphertext. And I can send all these ciphertext over the network. My friend will have ciphertext. It will apply the key on the algorithm and can derive plain text for each of these blocks. Now, what is the problem here? Why I'm saying it's not secure? Let's look at this. Strength is a very simple algorithm. Right? You have to apply same process on all the blocks. Allows for parallel encryption of blocks in a plain text. So blocks are not depending on each other. They can run parallelly. They can send it. At the recipient, it can decrypt it. But the only thing it need to do, arrange those blocks in a sequence so that you got the original message correctly. That's the only thing. Yeah. Can tolerate loss of damage of block. So if let's say second block doesn't reach to the recipient, it doesn't impact on the third block. Third block can be recovered correctly, despite you don't receive second block. What are the problems? It says documents and images are not suitable for this. Why? If you are encrypting same message, again, you got the same ciphertext. So let's say my plain text is Himachal. I'm using key X. I will got some ciphertext. Again, in my sentence, there's another Himachal, same key, same ciphertext. Yeah. So if I'm encrypting an image, something like this is the encryption. So I will see that these part and this part exactly same. You know, 2 eyes, 2 hands, 2 legs, all same. So I can see that within the ciphertext, this pattern is similar. If I know this, I'm already automatically know others. Right? That's why we say this is not safe. In documents, in images, whenever there's a same word repeating again and again, you got to see the same ciphertext, which will allow attackers to get some information out of it. And we don't want this to happen. So there's another mode called CBC, cipher block chaining mode. What it does, it interconnect blocks, says the outcome of first block input to this. So we shuffle the plain text, we perform an XOR between the plain ciphertext of first block and the plain text of the next block, and then pass this as input. Similarly, the outcome of this XOR with this, outcome of this XOR with this. Yeah? When you go to the ciphertext, you got the key, and then you get the plain text. Now, how you start it? So generally, we use random number that we call initialization vector. You can pick any number, any random number that you can XOR for the first block, get the ciphertext, but then the ciphertext is become this number for next block. Similarly, when you're decrypting, you use that same number, random number, to derive this. But then for next block, you decrypt it and then XOR the ciphertext to this outcome to get the plain text in a similar way. Right? So what we are doing here, if my input text is same here and here, my ciphertext different because it's an outcome of this and this. So this value, this input is different from this input. Even the message is same. Right? So every time your ciphertext could be different even if this plain text is same. And that's how it solved this problem. It's one of the popular mode. That's how we do it. Strand doesn't show patterns in plain text. It's the most common mode, faster and relatively simple. What are the drawbacks? It says require reliable transmission of all blocks sequentially. If you lost one of the blocks, it will impact the next, yeah, and others, because the outcome of this is feeding the input to this, and so on. CBC is not suitable for applications that allow packet losses. If you're listening to music and suddenly every other few minutes, you don't like it. Yeah? If you're watching a video, image just suddenly got distracted. You don't like it. That's why we don't use it here. It is good in the application, for example, text-based. But in an application where you can't tolerate packet losses, it's not good. Then we got CFB mode called cipher feedback mode. What it does? Now you see one of the difference here. For these modes, you got the same algorithm. It says encryption here, also say encryption, not saying decryption. So if you look at this, we have encryption and there's a decryption algorithm. But here it just the same algorithm. We don't need two algorithms, just one algorithm. What it does, you got a random number, we call it initialization vector. You pass this number to the algorithm, get the key. Whatever output you are getting, we are doing XOR here. We are not doing XOR here, we are XORing after the outcome. And then the outcome of this is input to this block. That's why we are saying cipher feedback mode. It's a cipher feedback. Cipher is this. The final outcome is the input to this block. Similarly, the final outcome is the input to this block, and so on. We are repeating the same here. It's just the difference is, instead of, since you have ciphertext, you XOR it, get the plain text at this point. So use the same initialization vector, get the key, algorithm. This process is exactly same. For encryption and decryption, you know plain text here, you can derive ciphertext. You know ciphertext here, you can derive plain text here. Yeah. For next block, the ciphertext you're passing here, you know the ciphertext, you can pass it here to get the plain text and the ciphertext the next block, so on. So this block gives you a little flexibility. You are using the same algorithm, And then some things that you can pre-compute. This and this exactly same. Now there's another block, another mode is called, output feedback mode. So what's the difference? Rather than using the cipher mode, the cipher value, I'm using output mode. Before I XOR it, I'm just using this value. Earlier what we were using? The final outcome. That's why we are calling it cipher feedback. I'm using the final outcome, ciphertext, as a feedback to the next block. But here I'm using output of this, not the cipher. Of this block to the next of this, outcome of this, next to this, and so on. Which is better? Cipher feedback mode is better, or output feedback mode is better? What do you see, and why? What do you see any difference here? What is happening? So in this block, you know random number. For example, you don't know the plain text. Yeah, you have to encrypt. Let's say you have to encrypt after an hour. After an hour, someone will come saying, encrypt this message. And this is part of the algorithm. You know the random number, you know the key, you know the algorithm. You're just waiting plain text to come, right? When plain text comes, you derive ciphertext. Now this block is depending on outcome of this, not the cipher of it. So you can pre-compute this part. You can pre-compute this part as well. And you can pre-compute this part. So you can pre-compute everything. As soon as you got the plain text, you just XOR it to get the ciphertext. You got this, you got this. Yeah. This block is much faster, not sort of waiting plain text to come. So you can pre-compute everything, the whole part. You can pre-compute this part, you can pre-compute this part. As long as you know the number, you know the key, you know the algorithm, you can pre-compute everything. And once you got the plain text, you just XOR it to get the outcome. Yeah. It's also relying on feedback mode. So even the same message comes up, it's having different ciphertext. But then it gives you flexibility to pre-compute everything. So it's much faster and real time. As soon as you got the plain text, you just XOR it and get the ciphertext. And the last mode we have is called counter mode. Counter mode, similar to first mode, but it does use counter as input. So you can generate a counter. You can nonce, generally we call it a random number. You can generate a random number and add some counter bits, and you keep increasing this counter every time, for example. Or you can use a random number as a whole. It's up to you. So I'm passing key. So what we were doing in the first block, we were having a plain text, passing the key, getting the ciphertext. What we are doing here, we have a random number, passing this random number. I'm encrypting this random number basically with the key. Once I got the outcome, I'm XORing plain text to get the ciphertext. And these blocks are independent. Independent means I can do this parallelly. If I have a message, I can run all together at the same time, because they are not depending on the previous block. There's no feedback loop in this process. Now what is happening here, even if you have the same plain text, you have a different ciphertext because this input is different every time. The sequence is different for every block. Yeah? Even if there's a slightly change of 1 bit, this outcome will also be significantly different from this one. And once you got plain text, you go to the ciphertext. This mode is also really popular. For any same type of input, you have a different outcome. This mode allows you to run parallel, so you can speed up the process. If you have to encode 10,000 of blocks, it's quite easy, quite fast. Yeah, so we pick these modes of operations. We don't pick first one anyway, but we can pick any of these depending on the applications that we are working on. Now, when we talk about the solutions, obviously we talk about, okay, this kind of encryption, these algorithms, blah, 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 we can do. When we design a system, secure system, what is one of the property we need to look into attacker's capability. I put a lock on this door. Yeah, I know only kids, for 5 years stay here. I might have a plastic lock that will work because I know the 5 years kid cannot break it, right? If this lock can be accessed by public, you might have double lock, triple lock, whatever. This brand, that brand. Why? Because you are understanding the capability who can break it and how they can break it. Similarly, when we design our system, secure system, we wanted to understand what are the capabilities of attacker. If attacker does this, is my system still safe? For what kind of attackers we are building these systems? So it's really important to understand this part. And in security terms, we have 4 different labels of it. The first label says collection of plain text, ciphertext only attack. What does it mean? We believe there are 2 users. User A sends a data, a message, over the network to user B. Message is encrypted. Any attacker can have access to that message. Means plain text, ciphertext. So now we believe that ciphertext, the attacker only has ciphertext, there is no other information. Based on that, you can design a system. Despite attacker having a ciphertext, cannot break it because it will not be able to decrypt it correctly. The second layer says collection of plain text ciphertext pairs, where we are saying attacker might have ciphertext plus having some knowledge of plain text ciphertext pairs. So let's say I have a list of 10 ciphertext and I have passed this to, for example, AES algorithm, and I know the ciphertext. So I build a table where I have 10 input plain text equivalent to ciphertext, right? And I have an 11th message that I have generated ciphertext equivalent, and I have give this to the attacker, the 11th message and the list of 10, the table that I have. Despite of having that table of plain text ciphertext pair, is it possible for attacker to break that 11th message? Can he crack that message despite of having some information of plain text and ciphertext? Attacker doesn't know whether it's been generated by AES or so. Yeah, we don't know. It doesn't know the algorithm, but it knows a pair. This plain text is equivalent to this ciphertext for 10 messages. And then we give another message asking it to crack it. Next layer says collection of plain text ciphertext pairs for plain text selected by attacker. So we have given what we said in label 2, attacker, but we also gave a black box to attacker, where attacker can input any message and get the ciphertext. Right? Based on that, can attacker crack the ciphertext that has been sent over the network? So you are increasing the capability and information and knowledge of the attacker. We are not saying, we are saying attacker might have ciphertext that we have sent over the network. Attacker might have pre-computed table of plain text equivalent ciphertext. I've also given a black box. Attacker doesn't know which algorithm it has, but if you give it a plain text, it will give you some ciphertext. Okay? With that one, can attacker crack it? And the last one says, instead of giving the black box of plain text encryption, we give other way. We give a black box where attacker can put any ciphertext and get the plain text. And we are asking attacker to crack it. Obviously, attacker cannot put this ciphertext, otherwise it will crack the problem. But not this message, but any other message. So you have increases the capability of attacker much larger here. And then we are saying, can we have a system in place that is still secure? If you achieve a security of this level, no one can crack it in terms of encryption also. But in the first place, we are saying attacker know only the plain text, doesn't know anything else. And then you're increasing the capability and information that attacker might have to crack it. So when we build a system, secure system, we expect the system that we have designed meet this level, at least level 3. where attacker might pick any plain text, give it to the black box, get the ciphertext, and now we are asking it to crack it. Given the ciphertext, can it crack it to the plain text? So that's how we design system understanding capabilities. In practicality, in real scenario, attacker might have some additional information, not just the ciphertext. Yeah? As an attacker, if you have to crack some ciphertext, you just Google it, get to know, who generated this, what type of data it had, what algorithm they've used previously, or if you know what the popular algorithm, you just want to run all the algorithm to see. But it has to be the other way. You got ciphertext and you need to crack it to the plain text. You don't know the key. You don't know the algorithm. Even if you know the algorithm, you don't know the key. Yeah. Now the second part after encryption. So encryption generally we achieve for maintaining confidentiality in the system. Second thing is about the integrity of message or data. Whatever we are sending, we want to ensure the recipient receives it correctly. If message or data have been tampered, modified in between, we have a process in place that can say this data has been tampered and we can discard it. Then we will not consider it. Yeah? For that, we use something called hash functions or hashing. What is hash function? Hash functions are called one-way functions. Yeah, one-way. Why? Why hash functions are so popular? Why we are talking about this? And they are really popular, like the XOR. Yeah, we talk about. Similarly, hash functions are also lightweight. They are part of many algorithms. Wherever we need to maintain integrity, wherever we need to check whether the data has been received correctly, we do use hash functions. Not really. Okay. Now one thing is, let's say I have a message of 500 bits. If I'm using a function that will ensure in some way that what I'm sending is correct, I might need another 500 bits. So I need to send something along with the message so that when you send two things together, the recipient can verify in some way that the message is correct because equation, this calculation is correct. The property, one of the key property of hash function is this one. Irrespective of the size of your input, there is always a fixed outcome. So there are hash functions that generate 160 bits, 224, 384, and so on. Irrespective, your message size is 100 bits, 1000 bits, 50,000 bits, 10,000, whatever. You're always sending a fixed hash code along with it. So it's saving your bandwidth, first of all. Right? Second, these functions are one-way function. If I'm passing an input to this function, getting the code, anybody having the code cannot derive it back. Having the code, you cannot recover the message. They always work one way. You cannot reverse them. And third, it's hard to find two inputs with the same outcome. If that is the case, this property doesn't hold. Yeah? So generally, the way we maintain or check the integrity, we have a message. Along with message, we send a hash code. So I pass the message to a hash function, a number of hash functions. You can pick any of those. We pass the input message to a hash function, get the code. And I'm passing this message and code over the network to my friend. My friend having a code and a message. And then my friend also know which function I have used. So he or she will pass the same message that he or she received to the same function, get the code, and match the code, the one I sent and the one she computed. If both code are correct, message is correct. It's not been tampered. Right? If someone is modifying message, this calculation will not meet. If you pass a different message to the hash function, you'll get a different hash code. and this hash code will not match with the one I sent it. So this is a simple, very simple property, and it's very simple way how you can check whether the recipient has correctly received your message or not. Simplistic example, you have fruits, put a jar, get the juice. From the juice, you can't have fruits back. It's as simple as that. So your hash function have to have certain properties like this. Now, what could go wrong? Let's say this. If you have a hash function of 2-digit, yeah, and I'm saying these digits are only binary. Binary means they can have only 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1, right? So I'm passing an input to a hash function, and it's giving me 2-bit outcome. Let's say for John Smith, it's whatever, 0, 2. For another person, it's a 0, 1. For this person, it's 0, 4. Now for this person, might be again the same. If you find for 2 different input, there's the same outcome, this hash function cannot work. Because if you know the code, you don't know the actual input. Might be the input was this, but then somebody start believing you that this is the outcome is the input was this. Because you are just, when you calculate this, as a recipient, you will have another message, passed to a hash function, you got the same code. So you end up believing that this message was sent to you rather than this one. So when we derive hash code, that's why we are saying hash code should be long enough. So at least, now we consider at least 160 bits long, so that there's no collision. For any 2 different messages, there should not be the same hash code. As long as you maintain this property, you can use that hash function. If any function that doesn't hold this property, we don't need to use it. Let's pick some example. Let's say consider the following 2 mathematical functions and explain whether they satisfy each of these property hash function or not. Multiplying 2 prime numbers together. We know prime numbers, yeah? What is a prime number? Divide itself or 1, yeah? So I'm picking 2 prime numbers, let's say 3 and 5, yeah? Multiply it together, become 15. Now see if it holds this property. For any 2 prime number, there's always a fixed outcome. Is it true? How it's true? If I have a prime number in 3 digits, for example, one 3-digit prime number, another 3-digit prime number, multiply, outcome might be 3-digit, 5-digit, 4-digit. If you have a 1-digit prime number, 3 and 5, you have 2-digit outcome. So the outcome is not fixed. Length of outcome varies, isn't it? Is it one way? If you know 15, can you factor it in 3 and 5? How easy it is. Now, in this property, it says, it doesn't say anything, but generally if you have 2 large prime numbers, it's really difficult to factor it. When we talk about the RSA, we'll see that. If you have, as I say, if you pick 3 and 5, it's easy. 15, you can even, just verbally factor it. But if I give you a number of 10 digits, saying this is the composite of 2 really large prime numbers, it's not easy to crack it. Yeah. What is the third property? For any 2 inputs, the same output. For any 2 different combination of prime number, the outcome is always going to be different. So it holds this property. It might hold depending on if we are saying large prime number, it might hold. If any prime number, it doesn't hold. And it doesn't hold this property anyway. How about the other one? Reducing a number modulo n. What is modulo n? What is a mod? Remainder. What is the use of mod? Why do we have seen mod in mathematics in many algorithms part of this again. What is the use of mod? Do we use mod practically in our real life? When there is a 13 hours in the afternoon, we call it 1 p.m. Yeah? What we are doing? We are doing mod. 13 mod 12, it gives you 1. 14 mod 12, it gives you 2, so on and so forth. Yeah? Why? Not negative, but we rely on 12-hour system. Yeah? So we have a group of 12, 1 to 12, and we believe outcome should be belongs to one of those. That's why we use mod. When the number goes beyond 12, we always perform mod to make it one of those numbers. Yeah? That's the property of a group. I have a group of numbers, and then people, there are properties of the group. If you perform certain computation, mod n, the number belongs to it. For example, I'm saying I have a group where I can perform addition over numbers. I have a group of 10, 0 to 9, or let's say 1 to 9, or 0 to 9, let's say 10 numbers. If I'm adding any two number, mod n, the number belongs to 0 to 9. So let's say you pick any, let's say 8 and 9. 8 and 9, 17. 17 mod n, 10, 7. Yeah. So this is the way how you can kind of reduce your outcome, or building improving your understanding of the outcome. In the mathematical system, there are many algorithms which are based on groups. Now, depending on the type of number you have, some group says we have natural numbers, we have integers number, we have square of numbers only. I might have a group that have square of each numbers. So it will have 1 square 1, 2 square 4, 3 square 9, 4 square, and I can do some computations over it. As an attacker, you need to know the group, first of all. In order to attack those algorithms, you need to understand how this group was formed, what those number belongs to it, what is the mod of that. Then only you can crack these, otherwise you won't be able to crack it. And that's why most of the mathematical algorithms use these group size and so on. Obviously, if there's an insider, because they might know some information, but it's still kind of very difficult for them to crack it. So that's why we use reducing a number modulo n. Let's see if it holds all the property. First one, for any input, it has a fixed outcome. Fixed outcome means belongs to the same range. Yes? Is it one way? If you're saying 13 modulo 12, which is 1, having 1, can you derive it was 13? No, so it's holding this property. Yeah? How about third one? For any two input, different input, does it have the same outcome? Why no? So when I'm saying 13 modulo 12 is 1, I can also say 25 modulo 12 is 1. Yeah? 37 modulo 12, 1. So if you know 1, it will be difficult for you to understand whether it was 37 or 25 or 13. So it doesn't hold this. That's why we have very different and complex hash functions. Some of these are like these. Now, earlier these ones are cracked. We don't use anymore. It's not been cracked, but it's been kind of we stopped using it. And now last three are the hash functions that we use generally. So SHA stands for secure hash functions, secure hash algorithm. SHA 256. So these number represents what is the outcome size. It generates a hash code of 256 bits, 224 bits, 512 bits, 384 bits. So we do use any of these hash functions. For any two input, for any two given input, it doesn't have the same outcome. Yeah. Now hash functions doesn't require any key. Now we want someone to generate hash function if they have some information. then only they should be able to generate. So I might have a key. So when I'm generating hash code, apart from the input, I'm also using a key to generate the outcome. And we call these functions MAC functions, message authentication keys. Yeah, everything is same, but they are using additional key with the input. So very similar thing, once the recipient receives the message, it will pass this message to algorithm, apply the key, get the code, and they'll compare the code that generates and the code that they received. If code matches, all good. If no, then means data been tampered. There's another called HMAC. HMAC is a double hash functions. So you're performing hash of a message with a key. Whatever outcome you're getting, you are passing this outcome to another function using another key to get the code. So sometimes we do use double hashing as well to make it more complex. Now, I'll talk about a few more things. Something is called authenticated encryptions. Now, there might be some requirement where we need to perform authentication and confidentiality at the same time. Yeah, how you meet that? So there are three ways. One is says MAC then encrypt. MAC, message authentication code, which is similar to hash function, but it does use a key. Yeah. When I say MAC then encrypt, what does it mean? It perform a MAC function first, and then encrypt it. So I have a plain text. I'm passing it to a hash function, applying a key to get the MAC, and I'm encrypting both together to get the ciphertext. Right? So in this case, I'm performing a MAC of plain text and then encrypting the entire message to get the ciphertext. Second, and this has been used in SSL, if you know what is SSL. Second says encrypt and MAC. So you got a plain text, you encrypt it, but you don't encrypt the hash. So you encrypt, you have plain text, you apply key, get the encryption, and you go plain text passed to a hash function with a key, get the MAC. So in this part, you are encrypting this part, not this part. What is the difference? What is the difference you see? Is there any difference? The difference is this: when the recipient receives this ciphertext, it doesn't know whether the ciphertext it receives is correct or not. There's no way to check the integrity of ciphertext. But if the recipient knows the key, it can decrypt it. Obviously, once you decrypt, you got to see plain text and MAC. So your recipient can verify whether the plain text is correct, this part is correct, but it cannot verify this part. So as an attacker, I might replace both things. If someone can replace both things, let's say instead of having message A, I have a message B, but I have correctly computed message MAC for this, and I can replace both things and send the same ciphertext, generate the ciphertext, send it to the recipient. There's no way recipient can understand whether this message is correct or not. It can look at this, whether this is correct or not. If I'm just modifying plain text, it will be caught. But if I'm replacing plain text, but also computing the correct MAC, the attacker cannot understand whether this has been changed or not. Right? In this case, when you send these two things to the recipient, a recipient knows whether this ciphertext is correct or not, because they can compute MAC, first of all, and then match it. Yeah? And then they can decrypt and derive the plain text. So again, depending on the applications, we have different combinations of this to use it. The last one says encrypt then MAC. What does it mean? So it's a plain text, you perform encryption. This one, you compute MAC over the encrypted data. So you're not passing the plain text, but you're passing the ciphertext to the function and getting the code. Yeah. Previously, in this one, we were passing the plain text to the hash. So you have to decrypt it, and then you can max, and then you can correct. But here you can, since this message was computed over the ciphertext, you can directly check. Yeah, so these are three kind of main differences depending on the applications. For example, this has been used in IPsec. What is IPsec? IP security, IP level security. It's also been used in TLS, transport layer security. What is TLS? Datagram transport layer security, which is being used for, it's a lightweight security, generally used on IoT devices. In IoT network, we can't, because of the constraint, we can't use traditional SSL or TLS. For those, they have a lighter version based on datagram, UDP rather than TCP. Okay, so the question is, should you consider faster but a weak security algorithms? Okay. What would be the scenario where you would prefer efficiency over security? No, I'm not talking about protocol, but the scenarios. Do you think of a scenario where efficiency is much more important than the security of the system? So in, for example, in power grid, in smart grid, as I said, there are some part of the system where devices are communicating and they need to send data in few milliseconds. And in order to send data in few milliseconds, you can't have any security. You can't apply encryption, whatever. If you do this, you won't be able to send it in few milliseconds because the availability is crucial there. They need to know the data. Even the data has been tampered, we need to pass this to the system and see if my system is unstable or not. If my system is still stable, I don't bother if the data has been changed. Yeah? Where would you prefer security over efficiency? For example, banking, payment systems. I want my detail to be secure. I can wait for a minute, maybe 5 minutes. Yeah? What is RSA? Right, so I can show you like these. So the three scientists from MIT, they come together and develop, 1977, they develop an algorithm called RSA with their surnames. Yeah, so one is Aldi Shamir, Ron Revist, Leonard Edelman. They come together and they published a paper saying new dimensions to public key cryptography. So as I said, there are two ways, broadly two categories. One, symmetric, where we use the same key for encryption and decryption. The other one is public key cryptography, where we use two keys for any user, private key and public key. Now the question is, why we need public key cryptography? Why can't we just have symmetric key? There's a way to generate key at the recipient end. Why can't we just use it? Why do we need public key system? Obviously, there are certain limitations in symmetric key. That's why we use another system. So what are those limitations? Any of those? So symmetric key system works when number of users are limited. For any 2 users, you need 1 key. If there are 10 users, you can compute how many keys. If 100 users, 1,000 users, 10,000 users, 10 lakhs, 20 lakhs, 1 crore. As the number grows up, number of keys grows exponentially and become much harder for you to maintain those keys, remember those keys, and regenerate those keys. Yeah, it's very, very difficult. If I need to talk to 50,000 users, I need to have those keys, 50,000 different keys to maintain. Yeah, it's too complex. Rather than I use this method, what I will do, I will have 2 keys. I'll give you 1 key. I'll keep 1 key for myself, private key. public key, you can send me anything with that key, and I can decrypt it with my key. As simple as that. For any user, I can give my public key to all of you. You can send me, and I can use my key to decrypt. Yes. I don't need to have thousands of keys. I just need to know one key, and I need to give you another key, public key. Yeah, so for any user, you can have just 2 keys. You can give the public key to anyone else who want to send you the message, and you can use the other key for you to decrypt it. That's where public key cryptography got really popular. It's very widely used for large systems. For any large system, you'll see they have public key cryptography. Now, recently, again, we said that this algorithm, since was developed in 1977, how many years now? Around 50 plus years. In the last 50 years, this is still secure. No one could crack it, where there are a number of algorithms have been cracked. Recently, Chinese scientists claim that they have broken encryption, RSA encryption, with a quantum computer. Now, how do we understand a particular algorithm is secure? What are the key things that makes these algorithms secure? The most important thing is the key and its size, more importantly. For example, password. 10 years back, we used to have 4 or 5 digit passwords. Yeah, mostly people have password with their pet name, school name, surnames, date of birth. I don't know, many of still have, but then over the years, we learned that these are the weak passwords. And from the breaches, data breaches, we have learned that we need to have more complex passwords, because security system has changed. We have got new capability. There are tools that can crack your password in a few seconds. If you have 5-digit passwords, they just literally crack it. So we said, oh, you have to have 8-digit password, 10-digit password, 12-digit password, lowercase, uppercase, special symbols to make it more complex. Yeah? Okay, let's understand this. I have a 4-digit, let's say I have a 3-digit password, and it's a binary number. How many possible combination will have? 8. So in order to brute force, anyone needs to apply 8 possible combination, and the solution will be one of those to crack it. If I have a 10-digit number, how many combination? Binary, 2 to the 10. If I'm saying it's not binary, it's decimal. How many? 10 to the power 10. I'm saying it's not just number, it's a lowercase, uppercase as well, which is 26 letters, yeah? Uppercase 26, 26, 10. How much? 62, 62 power 10. If you're also using special symbols, that's a 10, saying 72 power 10. So you're making this more complex, the possible combinations for attacker to crack or to guess. So the input size is also varied. It's not just the length. Even if you have 8-digit, if you have a lot more combinations, you can make it more complex for attacker to crack it. That's where the recommendation practice is. You have to have 8-digit, 10-digit long password, but then make sure you have uppercase, lowercase, some combinations. So that even if you are using any of those tools, it will take years for them to crack. And hopefully, by those years, you will change your password. Yeah? There's a saying, you just change your password like the toothbrush every 3 months. Most of the people don't change it, but hopefully they change in every year or so. So with the same understanding, for any algorithms, as the computational power increases, the security that we are talking about now may not secure in the future. People are talking about quantum computers. One of the properties saying quantum computers are really powerful computations. They can crack the algorithm that we cannot crack as of now with the hardware that we have. So these RSA with the same size, AES with the same size, might not be secure in the future. So security is a relative thing. As I said, if you put a plastic lock and there are 5-year kids around it, they won't be crack it, so you're still secure. So it's all relative, depending on the capabilities of the attacker. Similarly, the algorithm we are talking about secure with the quantum computations, they might not be secure in the future. So in the future, you need to revise the thing. You need to maybe make the key length larger or different combination or something to make it more secure. So they said that they have cracked it. Now when people look at this, actually what they did is they look at where is this? They pick the 50-bit integer and they test it, and they are able to crack RSA with a 50-bit integer size. Now, but generally when we pick RSA, when we talk about prime number, the recommendation is we should have at least 1024 bits, or good practice having 2048 bits of size of a prime number. Somebody is cracking with 50 bits, doesn't make sense, because we don't use 50-bit prime numbers anyway, right? So in the future, when we have a computation where people can crack 1024 bit, I might go to 30848 or some other numbers. And with those capability, they won't be able to crack it. So this is a standard, and that's why we have standard bodies. Those always revise these documentations, understanding what the capabilities we have as of now. Yeah, so they always recommend use different sizes, different things altogether. What is RSA? Okay, how can you crack it? So one of the things is, if you are really following big numbers, complex things, you can't crack it. But what is the way of cracking it? If I have a, let's say, small number, how can I crack it? What is the principle? What is the property of this algorithm? If you break it, it will crack the algorithm. Okay, say to select two large primes. So let's go to the algorithm. Say to select two large prime numbers at random where p is not equals to q. So I might have 10248 bits long, one prime number, another prime number, where their two numbers are different. I might multiply them. N equals to p times q. If I know p and q, I can perform easily p times q, not an issue. Then I need to select something called phi n. Phi n is if p and q are prime numbers, I can easily compute p minus 1 times q minus 1. Yeah, knowing I know p and q. Easy to derive n, easy to derive phi n. Now you need to select, as I said, public key system has two algorithms. You pick two keys. You pick one key and you derive the other one. So let's say I'm picking one key between 1 and phi n, this number, any key. And there's a consider a property called GCD, which is the common greatest common divisor of this number, and phi n should be 1. So there should be prime number, relative prime to each other. So let's say if my number this is, for example, 17. 17 is a prime number. Let's say it's 18. So E should not be a factor of 18. Factor of 18? 233. Yeah. So my E should not be. It should not be either 2. It should not be either 3. It should not be either 6. It should not be either 9. Any combination of the factor. I can pick 7, for example. 7 is relative prime to 18. There's a common factor between 18 and 7 is 1. So you can pick any number like that, right? And then once you pick E, you can derive D with this equation. For example, you know phi n, you know E, k could be constant. Yeah. So this is something called multiplicative inverse. I'm not going to detail, but let's assume we can easily derive it. Yeah. Once you know E and D, you can phi n and E, you can derive D. So you already have pair. Let's say public key E comma n. We already know E, we already know n, and the private is D and n. Right? I will publish this number. Anyone who wants to send me message, and I'll keep this secret with me. Now, what is the catch here? I'm saying anyone can know E and n. What are the things that they cannot derive out of it? What do you need in order to crack it? let's say attacker also know this. Can they crack it? What they need to know in order to crack it? Or what additional information they know apart from E and N? Sorry? What? And again, if you know the public key E and N, you know the message M to the power E mod N, you know already E and N, you can compute ciphertext. If you know the ciphertext, you can compute C to the power D mod N. Yeah, easy to go. But how can you crack it? You need to know phi n. What I'm doing, I'm just computing phi n, keeping it secret. If you are able to crack, another way you can think, if you are able to crack this, you know n already. If you are able to crack n into p and q, you can compute phi n, you can crack the algorithm, right? But that's one of the reasons we say you have to have large prime numbers. Even if you try to break them, the current computational capability will not work here. If you're picking small numbers, easily can crack it. Yeah? So it's all about relatively. What capability we have as of now, based on that we define security of the system at present. And then there's what is PKCS? Public key cryptographic standards. So this is developed by NIST in the US. They release recommendations. If you are using, for example, AES, use in this way. If you are using RSA, use some padding. If you are using Diffie-Hellman, so they kind of do some recommendation. What should be the size of the keys, and so if you're following this, you are up to date. Okay. Now, in the smart grid, we talk about one of the problem is default passwords, right? I say there are IoT devices which are having either no password or default passwords. If you are able to crack one of the devices, you can crack all the devices. So what could be the solution? How can you think of? So there's a scenario where we have different types of devices. For example, we have IEDs, we have what else? We got smart meters and so on. You got smart meters. So you got a generation unit, transmission unit, distribution coming to your home. You got a smart meter at home, and there is a control center, and you have authentication server, for example, here. Now we say that default passwords are there, but in organizations we have users with different roles. So there might be users, somebody is calling as security officers, there are vendors, there are management, maintenance personnel, they do all kind of maintenance. So if you're deploying large number of similar devices, if one of the keys is compromised, one of the device compromised, says like all the device will compromise. So what kind of solution you can think of? What should we do? How you solve this problem? How you make sure that if one device is compromised, others are still safe? What information you will add? What you can think of? It's not too complex, just think about whatever, how you distinguish between devices. So let's say they all have default password, but what extra information I can attach to each of those devices that makes us kind of unique or different. Maybe you can solve it in a new way. So I give you 50 of devices. They all having default password ABCD. I want to deploy them, yeah? Now the question is, my worry is about if one of those is compromised, they all be compromised. What should I do? And there's no way you could change the password because they are hard-coded password. Those passwords are created at the time of manufacturing of those devices. So you can't go and change the passwords. Google it. See if you can think of any solution. You should build this habit to Google. When there's any question comes to your mind, just Google it. Get something out of it. What people are saying. I'm talking about something, but that could be very different than what you can find. And these are really kind of research problems. If you're able to address these problems, you're solving a really big problem, scalable problem. You could have project like for your undergrad, master's, PhD, whatever. This could be part of it. How you build a system that can solve these kind of problems. So there are some guidelines from NIST which says we need to authenticate and authorize devices in such a way that resources access is specific to a user, information is not shared among users, and the control of authentication, authorization is hierarchically managed by substations and the central station. But the problem is we got default passwords in those devices. We got multiple passwords for a specific user role. For security officer, there's a password. For vendor, there's another password, and so on. Whoever claiming as a vendor can have that password, and they can access devices. So our worry is not like they have default password, but our worry is more if one device is compromised, it will compromise everything else. And there's no way you could change those passwords because they are hard-coded passwords. What did you get? Does it say anything online? Google? Yes, multi-factor authentication could be one of the simplistic way. What else? But how does it solve? Let's say we apply multi-factor authentication. What will happen? So let's say I enable multi-factor authentication on a device. Yeah. Whoever holds that device can accept. But how does it solve? Any person, if I'm holding device, I can accept or reject. He can do the same thing. You can do the same thing. As long as you have access to that device, you can do this, yeah? Does it solve problem completely? What else? How can you customize this multi-factor, let's say? This could be one of the solutions, but how can you customize? How can you make sure that you should also be able to identify who is that person accessing the device? So the way I have designed this is, I said there's an authentication server at the control center, but then you also got one hierarchical, because that's what has been recommended on substation, authentication server on each of the substation, depending on how many substations you have, so that you can control all the users and all the devices of that substation through this server. Yeah. So if there's a user belonging to this substation needs to access any of those devices, then you need to go through this path. Because this server will not be able to authenticate that user. The user belongs to here. So your request need to be forwarded here. and then it will approve or disapprove, whatever. And that's how it works. When you go to roaming area, you got a cell phone, yeah, you're going from Himachal to, let's say, Delhi or to south. When you turn on your cell phone, you are authenticated with the local network. There's an authentication server that looks whether your SIM belongs to this network or not. If yes, then you're authenticated, you can make calls and whatever. But if you go to south, let's say, how does it work? So you're connected to their local network, and that network will send requests to this network where your SIM belongs to. And this will, and generally what happens is they send some tokens, approved tokens to the server. If you're living in that area, again, let's say for a few days, it's not like whenever you're connecting, every time your request is coming back and forth. It will give you a set of tokens sent to the server and then locally verify it. But at least one time it will send this request to your local server. Server will generate authenticated tokens, send it to you. Every time when you send this request, it will authenticate based on the tokens. So in the similar approach, you have to follow this. Now what I said here is, so let's say this is the scenario. I got multiple devices, D1, D2 up to DM. I'm saying they are management personnel. They are people who are having one type of password. They are security officers having one type of passwords. Vendor engineers having one type of passwords. Now the problem is, if one type of password is leaked, all these devices will be compromised with this user role. Yeah? The way I'm going to solve, and the way I can think of, whatever password I have, I'll just pass this password and compute a hash. And along with password, I will put certain other parameters. One of the parameters could be location of the device. So if I'm deploying a device in this room, for every device, the points are different, for example. Yeah? And if I'm computing this value will be different for all the devices. So if one device is compromised, my other device is still safe. So kind of this could be one of the solutions, but there might be multiple solutions that we can think of. Sorry? 1 o'clock, no? Okay. So we'll be, okay, let me just give me another minute and then we're done. So we say, just let me know, yeah, because I don't know when your class is up to. So let me know when to stop. So attributes, mode of access, whether you are accessing a device in person or remotely. If I'm using a device in person, I might not need certain parameter, but I'm using it remotely, I might need some additional parameter to prove that I'm the right person who is accessing this device remotely. I'm not on campus. Where you belongs to, location, and some other secret parameter, some individual ID or whatever. So you pick some combination, pass to a function, get the hash code, and this will be kind of a unique combination for in terms of devices and then who is using it. And you can compute this on the go. The system can automatically recognize the location, the role, another parameter. Yeah, so that's how you can, right, so we'll stop.